Okay guys, let's take a look at today's lesson. We're actually going to be adding on two more tests. We're going to be looking at the direct comparison test and the limit comparison test. So the direct comparison test, let's actually talk about that one first. One of the criteria is that our a sub n term has to be positive. We know what the a sub n term, right? That's the nth term, what we're taking the it generates the sequence, and this summation makes it a sum. Right, so this is the problem that we're going to be given. The a sub n is what we're going to be given. When we do the comparison test, we have to choose another series to compare to. We're going to call that our b sub n. Okay, so this is what we're given. That's what we are given. That's the problem we're trying to work, is the a sub n. The b sub n is what we choose. We're going to choose this series, and this series has to be very close to the series that we're testing. I mean really close, like almost exactly the same, with a few slight variations, and I'll talk about how to choose the series that you're going to compare to, but they do have to be very close or this test does not work. And let me just caution you about this particular test, the direct comparison test. This is, students tend to like this test. I think because it probably doesn't take very long, but it is dangerous. Just going to throw that out there. If you like living on the edge, this is your test. Okay, direct comparison test, very dangerous, and I will explain why. If the inequality does not go the correct way, the test does not work, and you have to scrap it and do something different. So that's the danger of this test, is if the inequalities don't go the way we need them to, then the test doesn't work. Now, I say this to students every year, please beware of the direct comparison test. Every year I tell them the dangers, and I still have students just blindly going in. And I will tell you, about half of the time when a student uses the direct comparison test, the inequality is wrong, going the wrong way, so therefore it fails and they think that it works. So please be careful. So let's go through. How do we know? First of all, again, a sub n is the one that we're trying to prove convergence or divergence of. B sub n is the series that we're going to choose. So and the series that we choose needs to be easy to determine convergence on, like it's a p series or it's geometric. Really, those are the two main series that we use this on, is a comparison series as p series and geometric. So we find our b sub n, we determine that it converges. Okay, great. So our comparison series converges. What that means for us is that the series have to line up in this way. Our original one has to be smaller. It has to be smaller than the one that we chose, or this doesn't work. So if this is true, if the one we chose, the comparison series b sub n, is convergent, and the inequality works exactly like this, where our original series, the one we're given, is less than the one we chose, then our original series is going to converge. And this saying, I think, is quite helpful in determining the way that things are arranged. Less than a convergent series converges. Less than a convergent series converges. If this is wrong, and the inequality is the other way, where b sub n is less than a sub n, then the test fails. It doesn't mean anything else except it fails, and you're going to have to try something else. So at the very beginning, sometimes there's a little bit of sometimes like at term 1 and term 2, these might be reversed, but we're talking about over time, over the rest of time. Like if they were, let's say they were reversed, and at n equals 1, this one was larger, let's say. So then we would have to say at n equals 2, if it's from 2 on it works, then we would say, for all n greater than or equal to 2, then that would work. We would have to put that restriction on there. We have to say that, that for that, we're good. It doesn't work for the first term, but for all the terms after, we're good. So we would need to state that. And that would be unusual. It happens every once in a while, but that would be unusual. Usually it's consistent. Okay? So that's the criteria that we have to have for convergent. Now let's look at the other option. Let's say that the series that we choose, our chosen series, diverges. Let's say it diverges. B sub n diverges. And the series that we chose is smaller than the given series. Then our given series will diverge. And the statement that I think is helpful in this case is greater than a divergent series diverges. So those are like, it has to be that way. The inequalities have to be in that order or it doesn't work. And you have to try something else. If it doesn't work, that doesn't mean that, it doesn't mean anything except you're going to have to try something else. Okay, so if it doesn't work, what I would do, since we've already chosen a comparison series, is I would probably do the next test, the limit comparison test. So at least some of our work wasn't for nothing. I would probably just take that comparison series and try the limit comparison test. Okay? So let's go through and let's do a few examples of the direct comparison test. So here's our first series. We look at that and we think, well, okay, we need to think about something that looks really, really close to that, but it's actually like a p-series. Right? So if I were to kind of ignore this net plus 1, that would be a p-series, wouldn't it? So that's what we're going to do. We're going to choose that as our b sub n. But before we write anything, we need to write. I'm going to write that this is a sub n, and it is greater than or equal to 0. And then I'm going to say what b sub n is. B sub n is going to be 1 over n cubed, and it is also greater than or equal to 0. So I happen to be grading a problem. We had a problem that used a comparison test on the AP test last year, and that happened to be one of the ones that I scored. And if you didn't write this part, you lost a point. Just writing a sub n is greater than 0 and b sub n is greater than 0 got you a point, or part of a point. So that you have to write that part down. Okay? We have to write that. So this is what we're doing. We're saying that those things are true. And in fact, we can only use the test if that's true. Then if we have negative terms, we're going to have to go to a different test. Okay? All right, so this is the series we're going to use. We're going to write this part, the summation, the same way for our comparison series. N equals 1 to infinity of 1 over n cubed. And we're going to write it just like that. And now we have to judge convergence or divergence of our chosen, the one that we chose, that series. And really, if it's not easy to determine convergence or divergence, then you probably shouldn't use it or this test. Really, they need to be comparable to like a p-series or geometric, or really we should pick another test. All right, so this is a p-series. P is 3. 3 is greater than 1. Therefore, what do we know about p-series whose p is greater than 1? What do? They converge. So therefore, this converges by p-series. Okay, so I have determined the convergence of my chosen comparison series. Now we have to set up our inequality. So I'm just showing you all the work that you need to show. I mean, this is everything that you need to show. You need to show they're greater than 0. You need to show the convergence or divergence of the series that you chose. Now you need to set up an inequality. What I normally do is I normally put my original a sub n term first, and I put the b sub n term second. Do you have to do that? No. That's just normally what I do to try to keep it straight. Like I said, this particular test has really bitten me a couple of times. I am very, very careful with this test because it is sometimes difficult to tell which one is greater than the other one. Now what we're going to do, just looking at them, let's just kind of test some numbers. If I put a 1 in here, I'd get what, 1/9, oh no, excuse me, 1, I get 1/2 and 1, so this one is smaller. Okay, if I put a 2 in, I would get 1/9 over 1/8, and this one is still smaller. So it looks like, just by inspection, right, we don't have to write any proof about this, just by inspection it looks like this one is going to be smaller than this one. And if you think of other numbers, you see that is true. So let's see, we said that our chosen series converges And we have to be less than, our original series has to be less than a convergent series to converge. Is this true? Is our original series less than the one that we chose? Yes, so the test works. It works very nicely. So we say, therefore, converges by direct comparison tests. Okay, so there's one use of the direct comparison test. We have a few more. I am. On the daily work, I give you some to use it. Like I ask you to use it, which means that you can use it. So if I ask you to use it, that means you can use it. And you still have to show all the parts, but you don't have to be as cautious as if you're just choosing one in general to use. Then you need to be very, very careful. Okay? And you don't, in fact, I don't want to hurt its feelings, but I really just avoid using it unless I have to. Because telling whether one of these is large, in this case it's pretty easy, but sometimes it's difficult. It's very difficult to tell which series is larger than the other. If this test works, then the limit comparison test works, and that's the one I always use instead of this one. That's what I do. You won't typically ever be forced to use this. Okay, you can use the limit comparison test instead. All right, but some of us like living on the edge, and I'm probably going to see a lot of these on quizzes and tests. But that's okay. Let's look at the next one. So I've got to find a comparison series. It looks to me like if I just kind of, let's ignore the plus 2, because as we are going to infinity, as n gets larger and larger, really what does a plus 2 do to that, right? Not much, as n gets larger and larger. So I'm going to compare to 1 over 3 to the n. Or basically 1 over 3 all to the n. It's a geometric series. So I'm going to call this is my a sub n term, and a sub n is greater than or equal to 0. My b sub n term, I'm going to make 1 over 3 to the n. And that is also greater than or equal to 0. So I have everything, my criteria set up and ready to use the test. So after I set up that they're greater than 0, I go to the test. I'm going to write my series. I'm going to use the same summation notation that they used on the original one that I was given. So from 1 to infinity of 1 over 3 to the n. I see that that's a geometric series. So let's remember the geometric series test. What are we concerned with on the geometric series? R. We're looking for R, and we want the absolute value of R to be less than 1 to converge, right? That's what we're looking for. And actually, this R is 1/3. So the absolute value of R is 1/3, and that is less than 1. So therefore, this converges by geoseries. Okay, so the series that we chose is a convergent series. And so we want this to be true. We want our original one to be smaller than the one that we chose. So let's write them over here. I'm going to put the original one first, just again to help me keep things straight, and the test one second. So let's check that out. So if I put a 1 in there, I get what? This would be 1/5 and 1/3. Okay, this one's smaller. If I put a 2 in, this would be, what that'd be 1/11 and 1/9. Yeah, I'm comfortable that that is the way the inequality goes. Is that the way that we want it to go? Yes, it is, right? Because less than a convergent series converges. Our original series is less than the one that we chose, which was a convergent series, so therefore it converges. So therefore it converges, it meaning the original series that we were given, converges by direct comparison tests. Okay, one more. So this last one, let's ignore this -1 for we're looking for a series that is almost exactly like the one that we have, but is easier to work with. Right, so 1 over n to the 1/2, that's a p series, isn't it? So let's set up our our criteria. So this is a sub n, and a sub n is greater than or equal to 0. Notice that it starts at a 4. That's pretty significant for us to start at a 4, right? So that it's going to be positive. So we're going to say our b sub n is going to be 1 over the square root of n. That's what we're going to use for our comparison, and that is also greater than or equal to 0. All right, so let's work on our comparison test. So we're going to write the summation just like they did. We're going to start at 4 just like they did. So we have the summation from 4 to infinity of 1 over, I'm just going to write 1 over n to the 1/2. So that is a p series, right? P is 1/2. 1/2 is less than 1. Therefore, what do we know about a p series whose p is less than 1? It diverges. So therefore, diverges by p series. Okay, diverges by p series. So we have that part solidified. Now let's go to the inequality. And I'm going to write the original one first and then the comparison one. So let's test that out. We're going to start at 4 because that's where they started. If I start at 4, I get what over here? 1 and then 1/2. Okay, that's looking bigger. We can test another one. Let's test 9, just so that's a perfect square. If we test 9, I get what? 1/2, and I get 1 square root of 3, 1/3. 1/2 and 1/3. Are we comfortable that that's the way the inequality goes? So is this the way we want it to go? Greater than a divergent series diverges. The series that we were given is greater than the one that we chose. Greater than a divergent series diverges. So therefore, diverges by direct comparison test. Okay, so that's our direct comparison test. How are we with that? Okay. Now we're going to move to the safer, kinder test, which is the limit comparison test. That would be my choice. If I was going to do a comparison test, I would do the limit comparison test. So let's move to that. Let's check that out. Okay. So let's look and see how this test works. Again, critical, important, our a sub n is our original series, our b sub n is our chosen one, the one that we pick, the comparison. They both need to be bigger than 0, so it's the same criteria as the other one. So that's where that stops, so we get that criteria. And this has to be true. We're going to take the limit, the reason it's called a limit comparison test is because we're taking a limit, and we're going to make a fraction out of our a sub n and b sub n term. Now, this shows that a sub n is in the numerator and b sub n is in the denominator. It really doesn't matter. It really doesn't matter which way you do it. Whichever. You could flip them. It wouldn't matter. What's going to be significant is if our L needs to be both finite and positive. And let me just say, if L turns out to be 0 or infinity, then you've either chosen a wrong series or you've done something algebraically incorrect. Because this is going to, if we are able to use the limit comparison test, it's going to work. Okay, we should not get 0 because 0 is not positive, right? And we should not get infinity because infinity is not finite. So we should get a plain old number if we've done it correctly. Okay, so let's do that. So let's say this happens, so they're positive, we take the limit, we get L. If that is the case, then the two series that we have, the one that we were given and the one that we have chosen, either both converge or both diverge. They go hand in hand. Okay, they'll be the same. So let's take a look at our first problem. That just looks kind of like a mess, doesn't it? It's like, what is that? All right, so what I want you to do is I really want you to think about as n gets larger and larger. I mean, we're talking gigantic, right? In the millions, in the billions. This 10 and this 7 really aren't going to make any difference, right? They're really not going to make any difference. In fact, this n cubed is not going to eventually make any difference. It's these two that are going to carry the show, the n to the 4th and the n to the 5th. The biggest ones are going to carry the show, right? And so since this is what this series is going to look like as n gets larger and larger, we want to compare it with something that looks like this. So n to the 4th over n to the 5th, can we simplify that? Yeah, that's 1 over n. Right, so we're going to choose to compare to 1 over n because that is the closest we can get to something that a series that looks like this. So we're going to choose, so this is our a sub n, and a sub n is greater than 0. Our b sub n, we're going to choose to be 1 over n, which is also greater than 0. So see, we're setting those two up. No, you don't have to use the constant. You can if you want to. It doesn't matter. I wouldn't. I wouldn't use the constant. I would just keep it as simple as possible. So you can leave the 4, because the 4 has relatively little effect on the n to the 5th. Relatively little effect. Okay. So we're going to rewrite our comparison series. We're going to use the same sigma notation that they did. So from 1 to infinity of 1 over n. So now let's do the convergence or divergence of that series. That's our special one, right? It has its own name. You remember the harmonic series? Right? The harmonic series has its own name. This is p equals 1. And so therefore diverges by p series, or you could say it diverges because it's the harmonic series. It's that famous that you can just say its name. Okay, it's a harmonic series, so it diverges. All right, so let's set up our limit. So we're going to do the limit as n goes to infinity. We're working on this part right here. I'm going to go ahead and do what they did. I'll put the a sub n term. That's the one that we were given in the numerator. So n to the 4th plus 10 all over 4n to the 5th minus n cubed plus 7. That's going to be over our comparison series, which is 1 over n. So I'm going to rewrite that. Some of you can already see what the answer to the limit's going to be. It's fine if you just say equals the number. I'm okay with that. You don't have to rewrite it if you don't want to. But you do have to write this initial limit statement up. That's part of the test. Right? That's the test. Write the limit statement, then says equal. I mean, you can do it in your head if you would like. I'm going to rewrite it. So I'm going to flip this up. You know, this complex fraction, I'm going to fix it. So it's going to be n times n to the 4th plus 10 all over 4n to the 5th minus n cubed plus 7. Okay, so hopefully by this time in our calculus career, we could tell what the answer to this limit's going to be without doing any further work. Right, so this is n to the 5th on top and 4n to the 5th on the bottom. So our answer is 1/4. Our limit's 1/4. Right, we okay with that? And 1/4, we're still reciting the test. 1/4 is finite and positive. We write that down. 1/4 is finite and positive. Therefore, they're going to go hand in hand, right? Since our comparison series diverged, the other one is going to diverge. So therefore, diverges by limit comparison test. And there's our first limit comparison test. Okay? Let's do our second and last one. So we look at this, we say, well, I want to pick something really close. It needs to look really close to this, but it can't be that because we can't deal with this the way it looks. We know that minus 2 has relatively little impact on this a sub n term as n gets larger and larger. So let's choose to compare to 1 over n cubed. We okay with that? We're just going to do 1 over n cubed. So this is our a sub n term, and that is larger than 0. Our b sub n term, we have decided to make 1 over n cubed. So let's write our series from that. So again, we're going to use the same summation that they did. We're going to start at 2 to infinity of 1 over n cubed. What kind of series is that? It's a p series. So this is a p of 3, which is greater than 1. Therefore, what do p series do when their p is greater than 1? Yes, they converge. So this converges by p series. Okay, so I have a convergent series. Now let's do our limit. The limit as n goes to infinity. We're going to write out this right here. So 1 over n cubed minus 2 over 1 over n cubed. Okay, I'm going to flip and fix my complex fraction. Again, if you want to jump to the answer right here and just say equals the answer, you can. That's fine. I'm going to flip and fix it so it's n cubed over n cubed minus 2. And that limit would be 1, which is finite and positive. Therefore what? We converge. Therefore converges by limit comparison test. Okay, it goes hand in hand with the series that we chose. All right, how is that? Are we okay?